Go for it, Damien.
Oh, welcome everybody, and thanks for listening in on our talk. So we're going to look at the OpenACC, Open Accelerator speed up performance using the pgfortran or pgfortran compiler that my consultant Chris Scott, who's also going to co-present on this presentation, has also contributed majorly to. So we needed to come up with a better and more reliable way to calculate determinants. Let me just, I'm looking for a larger project, looking to support the speed up and scaling of a larger project, which is extracting de-efficient training and validation and test sample data sets from big predictive analytics data sources. And some example areas include supermarket discount card membership data, mobile app user data, web user data, and it may also be useful, and this is a bit of a long shot, but agricultural field trial design and analysis. Welcome any contacts. So the problem with the current split samples is that the predictors or inputs are often highly correlated, so that leads modelers to automatically throw away a whole lot of information because in their sample that they're staring at, a lot of the predictors are highly correlated. And we've got variable clustering routines to deal with that when we're routinely processing big data. But sometimes that doesn't always suit the problem or the business application problem area. And sometimes what we're interested in blows up into large numbers of dimensions. And there'll be some stakeholder somewhere in the supermarket who'll want to know all about that dimension that you can't throw away. And this is with the way I'm approaching it is this a way of finding de-efficient arrangements. So that exists already. This is not new. The modified Fedorov algorithm creates experimental designs for experiment designers to use, and that scales up well itself, up to the point where you have a lot of variables and a lot of interactions. So as I was scaling this up, I found very quickly on ordinary scientific computing workstations on desktops, I found there was a bottleneck of about 144 binary indicator variables, either availability or cross availability of, for instance, just strawberry yogurt stock keeping units in a strawberry category. So it's just the strawberry flavored yogurt SKUs. That quickly blows up and it gets up to the point where it's now becoming challenging. So how can we do that? Well, the bottleneck for this modified Fedorov algorithm is the log determinant function, and it's order 3 the way it's currently configured, and it quickly slows down, and it uses Gaussian elimination, reduced row, echelon form, various other ways you could describe the precursor of analysing a big matrix prior to calculating its determinant. There are slower versions that are slower than order 3 complex that try and accommodate for ill-conditioned data to some extent, but none of them seem to work fast enough or well enough in order to accommodate the large amount of ill-conditioning that we see in our big data sets. And so I've just pushed this main research to one side while we looked at the bottleneck. And I did some scholarly research and looked around on the internet, and I found that the Reverend Charles L. Dodgson came up with a good algorithm that later turned out to be able to be used in a way that immunized you against ill-conditioned data in your matrix. I'm not sure whether he was imagining application matrices as large as the ones we're working with when he wrote this, but it's a beautiful piece of writing. Anyway, and then if we skip forward, what is this, 152 years to 2018, we find that a group of programmers have parallelized this condensation method of determinant and log determinant calculation by using MPI and Fortran. And they use particular sized data sets, and they also chose as a test data set, pretty sure it's these guys or one of their related citations, chose the data to challenge this algorithm with would be infamously ill-conditioned, and it's known as in mathematical circles as the Hilbert matrix, and it has a particularly vile conditioning. So it's a good challenge data set to develop your algorithms with. Hey, Chris. Over to Chris Scott, who's going to take over the presentation from here. So just excuse us while I go to my meeting controls, and I guess it's that one, and I stop the share. Thank you. Try it again.
Thanks, Damien. I'll just quickly share my screen.
How are we going for time, Chair? We're doing all right?
Yeah, you're doing right.
Good.
Yep.
Okay, yeah, so thanks, Damien. So yeah, I'll just talk quickly about the sort of the GPU implementation, the initial GPU implementation that we did. So the starting point, as Damien already mentioned, was we had an MPI parallel version of the code, and we wanted to add in offloading to the GPU to try and get an extra boost in performance. The other good thing about this is that we can then have many different ways of running the code. So you can have, the MPI only, you can have a GPU only, or you could have a hybrid MPI plus GPU depending on what hardware you have available. So that's another nice thing of having these different options of running the code. And the option we chose for doing the GPU acceleration was to use this thing called OpenACC. And this is a programming standard for parallel computing, similar to OpenMP, which is maybe a bit more well known. And it happens to have really good support for NVIDIA GPUs through the PGI compilers in particular. And the nice thing about OpenACC is that it's quite simple and not invasive, in that you don't need to make lots of changes to the code sometimes to get good improvements. And it has good support for main scientific programming languages. A few different compilers support OpenACC, and it also has options like managed memory with PGI compilers, which greatly simplifies adding OpenACC into your code to get the boost from the GPUs. So over the next slides, I'll probably just talk a bit about the initial implementation we did and what speed-ups we got. And then I'll also look at some extra optimizations we did to try and get an extra boost in performance. Okay, but quickly, just a very, very high-level overview of the actual the algorithm, the condensation algorithm for computing the log determinant. So it's parallelized with MPI. So you start off with a big matrix, and you distribute the columns evenly among the MPI processes. And then you have the main loop, where you loop over all the columns in the matrix. And at each iteration of this loop, one MPI process does some calculations by itself. So there's a bit of a load imbalance. The other processes are sitting idle for a little while, but it's quite a cheap calculation. What we then do is we broadcast the column to all the other ranks, so they have this extra information, and then all the MPI ranks do some calculations. And this is the really expensive part of the operation. This final line in red, where everyone's doing this condensation calculation. That's where all the time is spent, or most of the time is spent there. So this is the part we focused on initially, or Damien focused on initially when he was converting to OpenACC. And the way that we went about doing this is we're using the PGI compilers, and we're using this managed memory option, which makes things a bit simpler. I'll explain a bit more about that on the next slides. And we're going to add in what's called a kernels block. So again, probably I'm just going to move to the next slide and just show you exactly what I mean by that. But this is a little sample of the actual code. So this is some Fortran code, and in yellow here, this bit really corresponds to the red bit on the algorithm before, which is where most of the time is spent in these nested loops here. And the only real changes that had to be made to use OpenACC in its code is this ACC kernels, these ACC directives up here. So it's just a few extra lines of code. And what this ACC kernels means is that when you add in the extra compiler flag to tell the compiler that we want to use a GPU, the compiler then looks in here and sees what can actually be pushed off onto the GPU. So what parts of this code can be accelerated. And it does that all by itself. You don't have to give it any more information other than just telling it, I want you to look in this part of the code. And it'll handle all memory copies from the device, from the host, from the CPU onto the GPU device. It'll handle all that by itself without the programmer having to do anything there. So It's really minimal changes to get this initial GPU version of the code. So just a few notes. I mean, I basically said this already. We had the kernels region there, which is where the compiler tries to figure out itself what can be parallelized. The caveat there is that the compiler might not always be able to determine whether a loop's safe to parallelize. The human might be able to see that it is safe, but the compiler might not be able to tell. In this case here, it was able to parallelize that loop. And we compiled with this managed option, which is using unified memory, which means that the programmer doesn't need to do any copies between the host and the device. The compiler will figure that out underneath. The caveat there is that it might end up doing more copies than actually necessary. So you might spend more time doing memory transfers than you really need to. There are alternatives. I mean, this isn't really an exhaustive list of things you can do with OpenACC, but instead of kernels, you could use a loop pragma, which actually tells the compiler you should parallelize this loop, and the compiler just assumes you know what you're doing. It doesn't do any checks there. And you can also use these memory copies, copy statements, which are where you explicitly copy data to and from the device. So maybe a bit more on that later on. And just some notes here about how we actually run with OpenACC and the PGI compilers on NeSIssity. So these are some initial timings from this, just adding those few extra lines of code. And what we can see here is that these are timings without GPUs and just running on 1, 2, and 4 processes. And these are the timings with the GPUs. And we have 1 GPU per process in each of these cases. So you can see with one process, looking at an 8,000 by 8,000 matrix was about 3 minutes runtime. And just by adding in 1 GPU and those few extra lines of code, we got a 13 times speed up. So it's a really good speed up for very little changes to the source code. I think that's a really important message. It's not too scary to actually program on the GPUs with this OpenACC. It's really nice. All these timings were done on Maharika, which is one of NeSI's computers, supercomputers, and we have these Tesla P100 GPUs, which are a few years old now, but they were really good when they were new. So they're kind of top of the range a few years ago. The other thing we can see is that actually, if you look at the scaling when you look at the timings without the GPUs, when you double the number of CPUs, you're pretty much halving the time. So it scales really well. This algorithm. You don't get quite as good scaling with the GPUs, probably because for the 8,000 by 8,000 matrix, there isn't enough work to make it scale up really well. But you still do get a really good boost from having the GPUs there. And this is just a bit more of the same. So, the 8,000 by 8,000 matrix we've already looked at, where compared to when you have 1 GPU, you get over 1.5 times speed up by going to 2 GPUs, and then it sort of levels off. If you look at a bigger array size, 16,000 by 16,000, when you go from 1 GPU to 2 GPUs, you're getting about a 2 times speed up to about 3 times speed up on 4 GPUs. And then if you go to, if you're interested in even bigger size arrays, 32,000 by 32,000 here, for example, if you go to 4 GPUs, it's 4 times faster than with 1 GPU. So this algorithm scales it really well, I think is the message here.
And Chris, what might be worth adding that the really big one, that's a really badly conditioned matrix. Boy, is that badly conditioned.
Yes, it's great that this algorithm can handle that. Yeah.
Can you see a question that has come up in the chat box from Alexander Pletzer? And he's asking, is this double or float precision?
It's double precision.
Double, yeah.
Okay, so quickly, I'm just going to talk about some extra optimizations we look to do. So we've got this really nice boost from some of the very small changes. Then we thought, if we actually look and try and do some explicit data copies ourselves, and handle and move more of the calculations onto the GPU. So before we just had these last couple of calculations on the GPU, but now we think if we actually move everything to the GPU, it's going to save us lots of data copies at every iteration. So what we can say that this does actually require more source code changes. So before we added a couple of lines, now we need to add a lot more lines to make this happen. And I can give you a quick example of what the code looks like, of some of the changes we have to make actually. So previously we had these 2 lines here, which were looking for the maximum value in a column, and getting the actual value of that maximum. to move this onto the GPU, we had to replace those 2 lines with these sort of 20 lines. So it wasn't quite as nice as when we just had to add a couple of fragments before. We had to do a lot more source code changes here. But what we can say is that we still got a pretty decent boost by moving these extra calculations onto the GPU and reducing the amount of data copies. We were able to get 1.5 to 2 times speed up for the smaller array, and even 1.2 to 1.4 times speed ups for the larger array sizes. And that's on top of the the 13 times or whatever boosts we had before. So it's a really nice improvement in performance, and it's probably a big enough boost that it's worth adding the extra complexity into the code.
And if Chris says it's worthwhile coming from a guy who's always adding about 30 lines of code to everybody else's program, that's probably saying something, isn't it? Are you sick of it, Chris? You're not sick of your job, are you?
No, this is really interesting.
It's been great working with Chris. He's made a fantastic contribution to the project, and it's really helped my learning of some of the important tools I need to upskill on. Thanks, Chris.
No, that's great that we're able to help. So Damien, did you want to say a bit about these last slides? Because
you're happy to step through them while I talk about them?
Yep, sure. Yeah.
Okay. So we just wanted to quickly check, do we get the similar scaling performance at the other end of the hardware spectrum, thinking there's some poor researcher out there who's got a slower CPU. Well, this CPU, in my dreams in 2007, I tried to get one of these on a server for my team, and I was denied because it cost 10,000 Aussie dollars. But this is what this older platform looks like. The Core 2 Quad Q9750 3 gigahertz processor, and we've got the processor upgrade these days only costs about $70, and the NVIDIA GT730 only costs about $70, so it's really cheap. And the description in the middle there, that means something if you look at NVIDIA graphics accelerators and scientific computation on them. But some of these terms have already been mentioned. Next slide, please, Chris. So this is how the total time for 1 through 4 CPUs, just using MPI. That's how it goes. So not as good as a supercomputer. We're not using nearly the same fabric or infrastructure, so that's fair enough. Next slide, please. Now here's 4 quite different configurations. We're just looking at the speed up, the multiply factor. So reference 1 is the execution on 1 core. This one here, number 2, that's with all 4 CPUs using MPI. That's the speed up. So we get it doubling. When we go to 1 GPU, but just adding those 4 kernel compiler directives for the PGI compiler, and adding the minimum amount of code and getting the maximum amount of remaining speed up, and that's what it looks like there, and a factor of 5. And now finally, if we go to the Chris's non-blocking algorithm and taking into consideration data locality and adding the approximately 30 lines of code, we get a further speed up there. So next slide, please, Chris. Yeah. So there's how the runtime decreases with that extra amount of work. So you see, like Chris said, it's worthwhile. I
think we're probably just about out of time, but yeah.
Yep.
I think the key message there is that with very little changes to the code, you can get really good boosts from using GPUs with OpenACC.
And what's the rumor from Alex about the C CUDA performance of the same compiler set being loaded? Is that his programs are running faster now as well with this?
I think with the PGI compiler seems to be
so we have some spin-offs with the project for other language users like CUDA C.
Great, that's fantastic. I've got a couple of questions, one from Blair and one from Wolfgang. Wolfgang is asking, did you see a performance difference between OpenACC kernels and parallel?
Oh, sorry, could you just repeat the question?
The question was, did you see a performance difference between OpenACC kernels and parallel?
We didn't do a direct comparison.
It's very similar, but there's a slight decrease in performance because the kernels knows more about the problem, and so it generates a two-dimensional or two-stage hierarchical computation structure inside the accelerator device, and it just edges in front in terms of performance. But if you're happy to blow away that, it only drops by 5 or 10%, I think, from memory, when I remember looking at it last.
Okay.
Something like that.
And so, And so Blair asks, like, related to the last question, I mean, on the CPU versus GPU speedup, was that 14 times speedup on a P100 versus a single Broadwell core?
Yeah, that's correct. Yeah.
Okay. And so he's asking that, curious about whether you tested scaling to a whole CPU worth of cores versus one GPU.
A whole node worth of cores versus one. Yeah, we did test that, but we didn't include the results here because we didn't have time.
The non-blocking code, the data locality sensitive extended code, that outperforms, because we get 2 GPUs per node, and when you harness them with the right, that provides the best performance. It's faster than if we used all the cores on the node, isn't it? Because that flattens out. Is that right, Chris?
Yeah, it probably is faster. I think that's correct. Yeah.
Yeah. Or good luck getting that test to run, because Mahuik is quite busy.
Great. Okay, so let's move on to the next speaker. And thank you very much for your presentations.
Thank you again.
Chris and Damien.
I'll leave.
That's fine. And please, okay, thank you. So Rere, it's your floor now.
Right. Rere kita, tau mai te manu ki takataka ki tō pai e. Tēnā tātou. Can you see that? Now I've shared my screen. Is that? Can people see that?
We can't see your screen though. Now.
Right now.
Yeah. Now we can see your screen.
Okay.
Great. Fantastic.
Tēnā tātou, ko Rere-No-A-Rangi taku ingoa, e uri tēnei no ngā roa hine nui. E mahi ana kei pōneke, so I'm a researcher at Victoria University. And pass over to Rhys.
Kia ora everybody, I'm Rhys. I'm a research fellow and working here with Rere on our project, which has had a few names. We called it Rere Ki Uta, we called it Kimihia Te Matangaro, and NeSIssity likes to call it Te Rere-No-A-Rangi, analytics to identify and connect successes to whenua.
Right. So we at Victoria University are working on a cross-collaborative project with University of Auckland and Taranaki-based Parinini ki Waitotara. So we're tasked with locating missing owners in Māori land. And so since the concept of ownership in Māori land or interest in Māori land is based on whakapapa, we are taking an approach where we want to reconstitute whakapapa as constructed by the Crown in order to build out a network, or more accurately like a graph, that will represent these relationships. The primary data set that we're working with is Māori land. And so this is just a screenshot of a block. If you've been onto Māori land online, you'd see Panihaka X. On the left-hand side is some vital data talking about the amount of shares, and below that says the amount of owners. So there's 3,800 owners in this one block of land. There are tens of thousands of blocks of land throughout New Zealand. So as you can kind of imagine, there are a lot of owners to different blocks, and unfortunately, the data that we're dealing with is ridiculously messy. I think we often say that if we were to clean the data, we'd have nothing left. So the way that we decided to do this was to undertake a record linkage exercise over the whole data set. So we used Python requests to scrape Māori land online data, encoded the JSON that we got into JSON LD, which is linked data, a variety of JSON. Our CRM CDoc was our particular flavor of ontology, of graph ontology, which is French, if I know correctly, which is an international standard. And that enables us to semantically express entities and their relationships within this data set. We used Apache Jenna to load our linked open data triple store, and then queried it with Sparkle. So how our pipeline is run is entirely within Docker machines that are built out of GitLab CI/CD. So some of you might be quite familiar with something like this, but maybe a screenshot is nice to look at, or maybe not so nice to look at. So we contained in our GitLab project wasn't just the code that we needed to run in our pipeline. It was also the code that we needed to build the images for our Docker machines. So as well as Python pip installs and et cetera, et cetera. So the kind of approach that we took was the infrastructure as code approach, and as Rhys put it, it was initially like using a sledgehammer to open a walnut, but as we needed to scale up, that became an integral part of the toolchain. And of course, here's some more. Here's the Docker file that we use as an example. I'll pass over to you.
The screen you're looking at is from Births, Deaths, Marriages Online. This is publicly available summary information, in this case of birth registers. We wanted to work with this information, so we wrote Python and exhaustively scraped this data. We encoded it using our ontology of choice, cdoc-crm, and generated RDF in JSON-LD. So the infrastructure that we developed for Māoriland Online really made this quite straightforward. At this stage, we were running on our on VUW's HPC facility, which is called Rapoi, and once we'd got our code running okay on a single year, we could straightforwardly use a Slurm task array to run 80 tasks to cover the years that we had available, which were the years from 1840 to 1919. We were loading all of this data into our triple store, and by the stage that we were harvesting this data, the load of our triple store, the load of about 100 million triples, was requiring that we use large memory machines down in Rapoi. I'll pass back to Rere.
So we were sitting pretty with Rapoi, and then unfortunately they, well, unfortunately for us, but fortunately for them, they, CAD or Centre for Economic Development here, needed to go they needed to pull down their HPC cluster and go on maintenance for 2 weeks, but maybe longer. They were unsure at the time. So we thought, okay, after we've already outgrown all of GitLab's free CI/CD cloud minutes, well, of course, we were completely dependent upon Rapoi's HPC cluster, and as well, being funded by NeSIssity, we were under the National Science Challenge. We don't get funding for computing resources, so we made the jump over to NeSI, and CAD helped us with the NeSI application, and within a week we were up and running, logging jobs, no problem. I guess the initial workflow that we had on Rapoi, all it needed to really happen was for it to be extended slightly. So instead of just using Docker machines, we were able to build a Singularity machine out of Docker recipe and then run Singularity on NeSI. So our pipeline or our workflow could just be extended slightly, and it would work fine. So that was awesome, really.
Yeah. We're not alone in our team, of course. We have some people that have dubbed themselves our data scientists, because they introduce doubt and probability. And I'd just like to explain what their really important piece of work is. That's that they were going to help us link the data that we were getting from Maryland Online with the historical birth data that we'd got from births, deaths, marriages online. Now, in order to do that, we grouped up in both of our data sets looking for people that we thought were, based on the structure of the data, were likely to be brother and sister, siblings. So we created 350,000 plus groups inside Maryland Online that we had reasonable suspicion that they were brother and sister. And we straightforwardly produced 420,000 groups out of historical birth information where it was likely that these children, these births, were siblings. The challenge for our doubter scientists, our Bayesian inference specialists, was to tell us which groups were actually the same people. And that we called that the challenge of the puzzles, to find a theoretically sound and computationally feasible way of figuring out which groups were the same. Just before we handed the puzzle as a monster pair of JSON files across, we thought we'd better know that there's at least one real linkage that we can draw. And my grandmother, my mother's mother, and her brother popped out at that point out of our data, and we promptly christened that the nugget. So the nugget, the B group is there, the N group is those names there, and the match, the linkage, is my grandmother, Ellen or Erna Morgan, nee Young, and her brother, Jimmy or Himi Young. So we thought with something, we know that with the right magic on names, and certainly this is something that a human looks at and says, those two are a match. And the importance of that for us is that that is information that is, if we can do this at scale, we have enormously increased the accessibility of the Maryland Online data, which is hugely fragmented. The scalability is going to be challenging. We ran some of Valerie's alpha code, a little piece of code in Julia, and we were able to reject edit distance name matching as being computationally infeasible because of the number of matches that we needed. Right, okay, to you.
Right. So we have spent a bit of time, and we've been lucky enough, or we've been given some platform to containerize some of our workloads, so Red Hat server, which means we can start building applications, containerized applications, which will effectively be client-facing web apps. They'll be able to access this triple store, this kind of large complex data store. And I mean, of course, the question is like, why, how? Simply, is that we want to keep our research partners happy. We want to provide them with a tool that can explore this data and extract, so they can extract value from it. A deeper reasoning as to why giving them an interface to kind of interact with this data is that the use of, or enabling the use of this triple stall is the best way to understand the meaning and the value of the data, and re-evaluate the semantic meaning implicit while using RDF ontologies. So what that means is we kind of have to sit alongside subject matter experts, people who are well versed in historical legal processes, who have worked at the Māori Land Court, for example. So one of our collaborators has actually spent time working or actually physically inputting this data 10, 15, 20 years ago. And all of those, I guess, parts of the puzzle mean that we can kind of create this feedback loop, which means we can better structure, better understand, and better encode the data to derive value out of it. Here are the 4 cowboys. You might recognise 2 of them. And this is in Taranaki, and I guess this is just an example of us constantly going back up to Taranaki and sitting with Adrian and Mitchell, these subject matter experts that we're talking about, and asking them these hard questions and getting harder answers back, and trying to encode that local knowledge into the way in which we comprehend the way that we encode this data that we're working with. As a side note, we've got 4 other data sets that we've kind of put into the same pipeline, and hopefully trying to look at potentially doing the same thing with other data sets and creating these kinds of groups, and looking for record linkages between records of identity. And of course, this is we're not alone, and these are the other faces that can't be here today and during this talk. They've got better things to do apparently. And this is the VIC team. And that's me. If you got anything else. I guess just to finish, I mean, our project so far has been an exercise in scaling up, scaling out, and portability, I guess. That's helped us adopt new tools, while actually enabling us to move closer towards our kind of shared goal, which is reconnecting whānau to whenua via whakapapa. So, right, clean up. Kia ora. Thank you for watching, and thank you for listening.